Welcome viewers to the second segment of the fifth lecture for the online series of lectures for the course of Dynamical Systems. Towards the end of the first segment, we proved part C of the results from for the example of negative gradient flows. Now, in this segment, we'll first state the result from part D, and then we'll prove it. Okay, let delta be a positive real number such that delta as obtained, delta positive be as obtained in the previous part, that is in part C. Then, for every point in the open ball of radius delta centered at 0, the forward semi-orbit gamma orbit of P, semi-orbit of P, gamma P plus, is bounded. Deduce, therefore, that omega of gamma sub P is non-empty. Okay, this is what we need to prove. Here goes the proof from the result of the previous part, that is part C. Part C, it follows that if P is in this open ball of radius delta centered at 0, then UP of T is in the closure of this ball BR0 for all T in the maximal interval of maximal interval of existence intersected with the positive real line. This is equation number 13. Now recall the techniques employed to prove proposition 2 in lecture 2. Okay, which was the global existence theorem 1. Okay, so now employ the techniques used to prove proposition 2 which was the global existence theorem. In lecture 2. Okay, so we are going to use it now. Let us first assume that the maximal interval of existence is the interval a comma b, with b being strictly positive and finite. Okay, then we are going to use 13, the result that we proved in part C. Okay, To conclude that, then we use 13 to conclude that norm of UP of T strictly less than R for all T in 0, B. Why? Because we have chosen JP to be A, B, where B is a strictly positive finite number. So the intersection of JP with 0, infinity is certainly going to be this half open interval. And by using 13 we arrive here for all T in this half open interval. Okay, good. I'm going to erase this part. Okay. Now use the results of proposition 1. Now use the results of proposition 1, which we call escape infinite time theorem. Escape infinite time theorem of lecture 2. Lecture 2 in this context, in our context, in the present context. That is, since B is a finite, strictly positive real number, there does not exist any epsilon, any positive epsilon, such that whenever T belongs to this open interval B minus epsilon to B, UP of T will not belong to this compact set, the closure of this ball BR0, which is of course a compact set. So we will not find any epsilon, so that whenever T belongs here, UPT will not belong in this closure. It will never happen. Because from 13 we have already seen that the norm of, which I wrote earlier, okay, yeah, the norm of UP of T is going to be strictly less than R for all T here. Since this holds, we will not be able to find such an epsilon. So let me write it here. Since for all T in this half open interval, already UP of T is in this compact set. So we will not be able to find such an epsilon. In other words, so what does that mean? It contradicts the result of proposition 1 of lecture 2, escape infinite time theorem. So it contradicts the result of escape in finite time theorem. In other words, let me write it here for the completeness. In other words, b less than infinity results in contradiction to the results declared by escape in finite time theorem. So the only possibility therefore is that b is equal to infinity. Okay, let me erase this bottom part here. Therefore, we see that Jp is equal to a comma infinity. Okay, and of course, because the initial condition for the underlying situation for the negative gradient flows was x at 0 equal to p, right? So which means that 0 is in j sub p, right? So since 0 is in j sub p and j sub p is equal to a comma infinity, it means that j sub p intersected with 0 comma infinity is going to be 0 comma infinity, this half open integral. Okay. In other words, u p of t is defined for all t here. Okay. Now recall that the forward semi-orbit gamma p plus is the collection of all vectors u sub p of t with t greater than or equal to 0. That follows from the definition of forward semi-orbit. Okay. Okay. Now this follows from the definition of forward semi-orbit. Now let us recall 13. 13 was the result that we obtained from part C. up of t is in the closure of BR0 for all t in Jp, J sub p intersected with the positive real line, right? That was 13. Now 13 affirms that u sub p of t is in the closure of BR0 for all t in 0 comma infinity, because we have seen that this is nothing but 0 comma infinity. Okay, so this is our question number 14. Okay, and this leads to the following fact. So the collection of all such vectors. The collection of all such vectors is nothing but the forward semi-orbit, right? So it follows that gamma sub p plus is contained in this closure, in this closure of the ball BR0. Okay, what does it mean? It's a compact set, and gamma p plus is contained in this compact set, meaning that gamma p plus is bounded. But this closure is a compact set contained inside the open set U. That is, follows from the hypothesis, that is, the closure of BR0 is contained in U as given in the statement of part C. Okay? Therefore, gamma p plus is contained gamma p plus is contained in a compact subset of U fulfilling the hypothesis of proposition 2 of lecture 4. Okay? What was the proposition 2 of lecture 4? Let me state it for you. It states that let theta from R cross U to U be a dynamical system on U, an open subset of R to the n, and P is in U if gamma P plus lies in a compact subset of U, then omega of gamma P, meaning the omega limit set of the orbit of P, is non-empty, compact and connected. So this is what we are going to use here now. Hence, the omega limit set of the orbit of P is non-empty. In fact, one can show that we can see in the course of the proof of proposition 2 of lecture 4. Let me write it here. In course of the proof of proposition 2 of lecture 4, that we omitted in the lecture 4. Okay. But if you go over the proof from the standard text, you will see that this omega limit set of the orbit of P is going to be contained in the compact set BR0. It is not just non-empty, it will be contained in the compact set in question. Okay, so QED. Now I leave it to the readers to prove the part E of the results for the case of negative gradient flows. Let me just state the part E. Let R be a positive real number as given in part C, and delta is a positive real number as obtained in part C, okay, from the continuity of the scalar function v at 0. This is how we obtain delta in part C. Now prove that for any point P in this open ball of radius delta centered at 0, the omega limit set of the orbit of P is going to be the origin itself. It's just the origin. It's the set containing origin only. Okay? So this is what you need to prove. So I leave it to the readers. Next we are going to discuss cycles and periodic solutions. Let's start with the discussion of cycles and periodic solutions. Okay, following proposition 2 in lecture 4, we revisited example 2 of lecture 3. We have seen there that the two-dimensional system dx over dt is equal to minus y, and dy over dt is equal to x, which we number as equation 16. Okay. So this is the example that we discussed in lecture 4, okay, following proposition 1. So this two-dimensional system has an orbit gamma sub 1, 0, That is, it's the orbit of the point 1, 0, which is a simple closed curve, So I'm writing the definition of a simple closed curve. A closed curve that does not self-intersect example, circle in R2 okay, so gamma 1, 0, which is a simple closed curve in R2, which is of course a circle in this case, gamma sub 1, 0 is the collection of all the points x, y in R2 such that x squared plus y squared is equal to 1, which defines a circle, right, in R2, centered at origin, and it is of radius 1. So it's just a unit circle. Okay, let me draw a couple of pictures in this connection. So say that this is a closed curve because it begins and ends at the same point. You put an orientation here. This is because it never self-intersects. It's a simple closed curve. A simple closed curve. Now let us draw the picture of a figure 8. Goes like this and then goes like that. It intersects. The curve self-intersects here. A closed curve, although it's a closed curve, but it's not simple closed curve. A closed curve that is not a simple closed curve, meaning that it self-intersects. Okay. Now let me define cycles. Definition. Cycles. An orbit of a dynamical system is called a cycle when it is a simple closed curve. It's called a cycle when it's a simple closed. That is, an orbit which is a simple closed curve is called a cycle. Right? Let theta from R cross U to U be a dynamical system in an open set U of R to the n. Suppose that for P in U, the orbit of P gamma sub P is a cycle. Okay, so we fix the point P in U so that the orbit of that point is a cycle, meaning that it's a simple closed curve, which is of course an orbit. Then there exists exists a positive number t, positive number big T, of course, such that theta big T comma P, theta is the flow, right, of the underlying dynamical system. By the definition of theta is of course the solution of u sub P at big T is equal to P, and where u sub P from 0 to T to big U is a parametrization of the orbit gamma P. In other words, this curve, right, from, now this is half open interval, to U is 1 to 1. So if I just exclude this right endpoint, then the curve becomes 1 to 1, and gamma P, which is defined as the image, I think it would be U sub P. U sub P. Okay. So the image of this closed interval 0 comma t under this map U sub P is nothing but the orbit gamma sub P of P. Okay. The function UP or U sub P is said to be periodic with period P. So this is the definition of a periodic solution, okay? And UP is called the underlying periodic solution. Now I am going to define periodic solution formally. Definition: periodic solutions let U being a subset of R to the n be open and F from U to R to the n be a C1 vector field a solution small u from the set of real numbers to the open set U of the differential equation dx over dt equal to f of x, which we denote by equation number 17, which is not an equilibrium solution. We already learned what an equilibrium solution is in the last lecture. Which is not an equilibrium solution. So it means that f of u of t, this is u of t means well, a vector here in this open set, right? And that cannot be 0, right? Since it's not an equilibrium solution. Since u of t is not, u is not an equilibrium solution, f of ut is not equal to 0. Follows from the definition of equilibrium solution. So this solution u is said to be periodic if there exists a positive real number t well, let me denote it by tau, a positive real number tau such that u of t plus tau is equal to u of t for all t in R. This is equation number 18. So this is the definition of a periodic solution. The solution that is not an equilibrium solution and that satisfies this periodicity condition. The smallest such positive number tau for which 18 this periodicity condition holds, for which 18 holds true is called the period of the solution. U is called the period of U. Okay, now we will discuss an example in the context of this periodicity and cycles. Okay, let me erase everything and work out the example. Example 1 of the 5th lecture. Suppose that the differential equation 17 so let me write down 17 for your convenience. Where is 17? The polynomial differential equation. This is 17. Suppose that this ODE has a flow theta from R cross U to U, and that the orbit gamma sub p for p in U is a cycle. Okay. Let t be a positive real number such that theta of t comma p is equal to p, we know that theta of 0 comma p is p, right? But we have this thing as well. Theta of t comma p is equal to p, and u sub p, the image of the solution as the time varies from 0 to big T, is equal to the curve gamma sub t. And finally, we want this map UP from the half open interval 0 comma t to the open set big U is 1 to 1. Okay. So this is going to be equation number 19, and this is 1 to 1. This is equation number 20. Okay. Keep track of these equations. We show that the function u sub p from R cross U, from R to U is periodic with period big T. Okay. So how do you do that? Indeed, observe that for any time theta of t plus small t plus big T comma p, from the property of the flow we know that this is the same as theta of small t comma theta of big T comma p, right? And from the hypothesis, theta of big T comma p is just p. So it follows that this guy is equal to theta t comma p. Right? We therefore, so we know that theta t comma p is u sub p comma t. We already know from the definition of the flow that this holds, so from which it follows that u sub p small t plus big T is equal to u sub p of small t. For all t in R, which shows that u sub p is periodic. Okay. Now we need to show that big T is a period of the solution u sub p. Okay, let us do it. So we again proceed by a contradiction and suppose that there is a number tau between 0 and big T, which means that a smaller number, smaller than big T, there is a number tau smaller than big T, a positive number, a real positive number which is smaller than big T, such that the following holds: u sub p t plus tau is equal to u sub p of t for all t in R. Suppose that such a tau exists. Letting t equal to 0 in this equation, equation number 21, we obtain u sub p tau is equal to u sub p 0, which contradicts that is which contradicts the fact that u sub p from 0 to t to big U is 1 to 1. This was one of the assumptions, right? This was given by equation number 20. And if this is the case, t belonging to this interval 0t, tau belonging to this interval 0 comma big T, satisfying this means that up is not 1 to 1 in the interval 0 comma t. Okay. Hence cycles, we just saw that cycles in a dynamical system correspond to periodic solutions, Okay. Good. So now we move our discussion to limit cycles. Okay. So let me get started with it in this segment. Let's see how far we can go, and the rest of the discussions will take place in the third segment. Okay. So let me erase everything. Let us get started with the discussion on limit cycles. And we open the discussion with an example. This is example 2 of this lecture. Okay. Consider the following two-dimensional system. Two-dimensional system. Okay, so let me write this ODE first. dx over dt is equal to minus y plus mu x times 1 minus x square minus y square. This is one equation. And there is another, since it's a two-dimensional system, dy over dt is x plus mu y times 1 minus x square minus y square. This is equation number 22. where mu is a real parameter. Where mu is a real parameter. Good. Oh, we look forward to understanding this system 22. To do so, we first look for the equilibrium points of the system, underlying system. Okay. We first study the underlying equilibrium points. Equilibrium points of this vector field. Minus y plus mu x 1 minus x squared. It's a 2D vector field. X plus mu y 1 minus x squared y squared. This is what we are going to do now. We will then look at the orbits and compute limit sets of those orbits. Okay. So to find the equilibrium points of this system, we solve the following algebraic system. Following algebraic system. Minus y plus mu x times 1 minus x squared minus y squared is equal to 0. We set it to 0 identically. We also set it to 0 identically, right? X plus mu y times 1 minus x squared minus y squared is equal to 0. Let us number this couple of equations, quadratic equations, by 23, and we'll study this quadratic system. Okay? Good. Let me erase this top part to create some room for me to write. Note that 0, 0 is the solution of the algebraic system 23. Is the solution to the algebraic system (23). Okay, and hence is an equilibrium point from the definition of an equilibrium point. Equilibrium point. So this is how we see that 0, 0 is an equilibrium point of the system. So we next check if there are other equilibrium points. We next check if there are other equilibrium points. So suppose that, so you see that if you take the whole R2, then you can have the x-axis and y-axis, two coordinate axes in this two-dimensional plane, where the two axes intersect at the origin 0, 0. We have just seen that 0, 0 is an equilibrium point of the underlying system. Now we will see if there is any other point except this point 0, 0 on the x-axis, which is an equilibrium point of the system. And we will also see if there is any point on this y-axis, lying on this y-axis, except for the origin at 0, 0. which is an equilibrium point of the system. These are the two things that we are going to do first. Then we will check if there is any other point here, which can be an equilibrium point of the system. So let us try to address these three issues. If there is any equilibrium point on this x-axis except for the origin, if there is any equilibrium point except for this point on the y-axis, then away from these two axes, if there is any other equilibrium point. So suppose that x is equal to 0 and x squared plus y squared is not equal to 0. What does it mean? X equal to 0 means you are on the y-axis and x squared plus y squared is not equal to 0 means that you are on the y-axis of the origin. Okay, so you can be anywhere on the y-axis except for the origin. So suppose we're dealing with that situation. Okay. So it graphically it represents a point in the y-axis, a point in the y-axis that is not the origin. So we're dealing such a point, right, on the y-axis. So it then follows from the first equation of 23. So since we are choosing x to be equal to 0, from 23 it follows that from 23 that y is equal to 0. Okay, since x is already equal to 0 and we have found that y is equal to 0, we thus have x squared plus y squared is equal to 0, contradicting the fact that x squared plus y squared is not equal to 0, which means that there is no equilibrium point at all on the y-axis except for the origin. Okay, so you cannot have an equilibrium point here or here or here. The only equilibrium point on the y-axis is the origin. Okay. Now, similarly, deal with the case when y is equal to 0 and x squared plus y squared is not equal to 0. Okay. What does it mean? Geometrically, it means that you are on the x-axis away from the origin. Okay, since x squared plus y squared is not equal to 0. So now, if you handle this situation and you plug in y to be 0 in the second of the equation number 23, then you see that x is equal to 0. And since y is equal to 0 and x is equal to 0, it means that x squared plus y squared is equal to 0, which contradicts the fact that x squared plus y squared is not equal to 0. Meaning that there cannot be an equilibrium point on the x-axis except for the origin. So this way we see that there is only one equilibrium point in the x-axis and in the y-axis, which is the origin itself. Okay, so let me erase everything. Therefore, let me summarize it. We get that if x comma y solves the algebraic system 23, and x square plus y square is not equal to 0, then one must have both x is not equal to 0 and y is not equal to 0. Let's see if there is any such point. So thus let x comma y be such a solution to 23, such a solution to 23 with x square plus y square is not equal to 0. So multiplying the first equation of 23 by x, so multiply the first equation of 23 by x and the second by y to get minus xy plus mu x square times 1 minus x square minus y square equal to 0, and xy plus mu y square times 1 minus x square minus y square is equal to 0. This is our equation number 24. So adding the two equations in 24 leads to mu times x square plus y square times 1 minus x square minus y square is equal to 0, which is equivalent to mu times 1 minus x square minus y square is equal to 0. Since we are assuming that x square plus y square is not equal to 0. So if we want to satisfy it, there are two possibilities. Either mu is equal to 0 or x square plus y square is equal to 1. Let us study these two situations separately. If mu is equal to 0, then one obtains from 23, let us recall 23. 23 was this algebraic system, minus y plus mu x, 1 times x square plus x square minus y square is equal to 0. That was one of the algebraic equations. And the other one is x plus mu y times, it's not a quadratic system, right, which I declared as quadratic earlier. It's a cubic system. Okay, whatever, doesn't matter. It's an algebraic system. That's the thing. 1 minus x square minus y square is equal to 0. Okay, so this was 23. Okay, so now plug in mu to be 0 in 23 and see that both x and y are 0, meaning that back to square 1, and this is again a contradiction. Okay, because we are assuming that both x and y are non-zero, so that x square plus y square is not equal to 0. Okay? So mu equal to 0 is not a possibility at all. What about x square plus y square is equal to 1? So if this is the case, then from the same equation, if I plug in x square plus y square to be 1, we get the same situation. Mu is equal to 0 and x is equal to 0, which is again a contradiction from the fact that x square plus y square is not equal to 0. Which means that x square plus y square is equal to 1 is not allowed either. What does it mean? It means that there is no equilibrium point of the system except for the region. So 0, 0 is the only equilibrium point of the system. Okay, so next goal could be to show that for mu strictly negative, so we have seen that mu cannot be equal to 0, okay? So mu strictly negative, and if P comma Q is inside this open ball, set minus the origin, then the omega limit set of the orbit of this point is the origin itself. This is what we are going to prove next. Okay, so I'll postpone it until the third segment of the fifth lecture. So thank you for attending the second segment.